Welcome to the video lecture on the complex plane and de Moivre's theorem. Recall that a complex number is anything of the form x plus yi, where x and y are any real numbers. If we let z equal to x plus yi, then we can show this geometrically as the point x comma y in the xy plane. So imagine drawing your axes and using x along the x-axis and y along the y-axis, and labeling this point z equals x plus yi. The x-axis we're going to call the real axis, and the y-axis we're going to call the imaginary axis. And this whole situation here is called the complex plane. So using this model, each point in the plane corresponds to a complex number, and every complex number corresponds to a point in the plane. We call it the complex plane. The x-axis is called the real axis because any point that lies on the real axis is of the form z equals x plus 0i, which is just equal to x. In other words, there's no imaginary part at all because the y value is 0. The y-axis is called the imaginary axis because any point that lies on it is of the form z is equal to 0 plus yi. So there's no x part, there's no real part, and it would be called a pure imaginary number. So let's plot the point 2 minus I in the complex plane. So all we have to do is realize that 2 is the real part, so we're going to go over 2 on the real axis, and the coefficient of the I there is a -1, so we're going to go down -1 on the imaginary axis and just put a dot at 2 comma -1. So this is the complex number 2 minus I. Now a definition that you need to know is that if we let, this should be a z, if we let z equal to x plus yi be any complex number, then the magnitude or modulus of z, denoted by these absolute value bars, is defined as the distance from the origin to the point x comma y. In other words, the absolute value of z, or this modulus or magnitude of z, is the square root of x squared plus y squared. And let's see why that is. If we draw our point x comma y over here, so z is equal to x plus yi, because it's going over x on the real axis and up y on the imaginary axis, you can visualize a right triangle where this leg is x and this leg is y. And by Pythagorean theorem, the hypotenuse would have to be the sum of the squares of those two legs and then the square root of that. And that is exactly what the distance from the origin to the point x comma y would be. So the distance between this point and the origin is exactly that hypotenuse. So that's where this formula comes from. It's just the hypotenuse of that right triangle. We call the magnitude of z the absolute value of z. Now remember, if z is equal to x plus yi, then its conjugate is called x minus yi. It looks exactly the same, but the signs in between are opposites. Now when we talk about a conjugate, we use this notation with a z bar. We put a little sort of line segment right above z. So if we take z times z bar, and that's what this is called, z bar, and that stands for conjugate. So if we take a complex number z times its conjugate, z bar, let's see what we end up with. We get x plus yi times x minus yi, so the complex number times its conjugate. And if we were to FOIL this out, notice that you do get a difference of squares pattern here. So x times x is going to be x squared. You'll get a minus xyi and a plus xyi, so those middle terms will cancel out. And then you'll get a positive yi times a minus yi, which would be a minus y squared I squared. And remember that by definition, I is the square root of -1, so I squared is equal to -1. So this turns into a -1 times that minus y squared, which turns it into a plus. It changes that sign. So when you take a complex number times its conjugate, you get x squared plus y squared. So that means that if we take the square root of that, product of z times its conjugate, that gives you that modulus. Remember, that's how we defined our magnitude or modulus of z. So this is just an alternative way of thinking about that formula. Now, when a complex number is written in standard form, z is equal to x plus yi, we say it is in rectangular or Cartesian form because the x and the y are the rectangular coordinates of the corresponding point in the complex plane. Now what we're going to do is we're going to transform this rectangular form of this complex number into its polar form. So let's draw our picture again. Here's this point x plus yi, or z is equal to x plus yi. And if we draw that distance to that point, we can create our little right triangle here. And in polar form, what we're going to call this hypotenuse is our r, and this angle here would be theta. And notice the relationship between r, theta, x, and y. Using just a little bit of trigonometry, we know this leg is x and this leg is y, and by right triangle trig, we know that sine of theta is defined to be the opposite side, which would be the y, over the hypotenuse, which is what we're calling our r, and cosine of theta is defined to be the adjacent side x over the hypotenuse r. And if we solve these for x and y, all we would have to do would be to multiply that r to the other side. So this becomes r times sine theta is equal to y, and r times cosine theta is equal to x. So that's what the Cartesian or rectangular coordinates are equivalent to. So if we take z is equal to x plus yi and substitute in now what x is in its polar form and what y is in its polar form, we get r cosine theta plus r sine theta times I. And if I factor the r out of both of these terms, we usually like to write it this way with that r pulled out front. The angle theta is called the argument of z, and there is a restriction here. We usually have to require that theta is between 0 and 2 pi. And the magnitude of this z is just r. So in other words, r is just going to be that x squared plus y squared. And again, we get that from the Pythagorean theorem using this right triangle. So the magnitude is the same as what r is going to equal. So for example, if we have z is equal to square root of 3 minus I, that's its Cartesian form, because you can kind of identify that x here is the root 3, and the y is that coefficient of the I term, so that would be negative 1. So that's its Cartesian form. And what we want to do is we want to change it so that we put it into polar form. So we want to put it into this r times parentheses cosine theta plus I sine theta. So all that requires is first figuring out what r is, and then figuring out what theta is, and substituting in those values. So how do we find r for polar form? Well, that's the fact that r is just that magnitude. So r is just the square root of x squared plus y squared, because it's just going to be that hypotenuse. So to figure out your r, you just take the square root of x squared plus y squared, and in our problem, the x is the square root of 3, and we need to square that, and the y is the negative 1, and we need to square that. So this is going to become the square root of square root of 3 squared is 3, negative 1 squared is 1, so we get square root of 4, so r is 2. Now we know what r is, now we have to figure out what theta is. So to get theta, we're basically just using these two relationships right here. So according to our right triangle diagram over here, sine of theta is going to be the y value, which we know is negative 1, over the r value, which we just figured out was 2, and cosine of theta is going to be the x value, which we know is root 3, over the r value, which we figured out was 2. So what angle between 0 and 2 pi has a sine value that's negative 1/2 and a cosine value that's root 3 over 2? Well, we know that that combination of having x being root 3 over 2 on that unit circle and y being negative 1, or y being positive 1/2, on a unit circle is normally a pi over 6 type angle. And we just need to think about which pi over 6 angle are we talking about based on which quadrant this is in. And you can think of this a couple different ways, but if you just visualize what the graph of this in the complex plane would look like, square root of 3 is positive, so it would be over here on the x-axis. Negative 1 for y is down here on the below on the y-axis. So if we were to plot this in the complex plane as root 3 minus I, what quadrant is that point in? That's in quadrant 4. So what's the name of the pi over 6 angle that's in quadrant 4? That's 11 pi over 6. And that's between 0 and 2 pi, so we want to use that version of it. And now all we have to do is put all the pieces together. Since we know r and we know theta, we're just going to rewrite it in our polar form. So our polar form looks like this. Z is equal to the r, which was 2, parentheses, cosine of our angle, which was pi over 6, plus I times sine of our angle. And that you just leave as is. So this is exactly equivalent to this complex number over here. It's just two different versions of it. This is the Cartesian form and this is the polar form. Now this time we're given our complex number in polar form and we want to turn it into rectangular form. So we're going backwards this time from what we just did. So first let's plot the point corresponding to this polar form. Z is equal to 2 parentheses cosine 30 degrees plus I sine 30 degrees in the complex plane. So how would you graph that polar form? Well, remember 30 degrees is the angle from the positive x-axis going counterclockwise. So we're talking about this 30-degree angle here, and the r being 2 is the distance between that endpoint and your origin. So this is that 2 right here. So this point right here is 2 parentheses cosine 30 degrees plus I sine 30 degrees. So that's its graph. It's just that dot right there. Based on this, we know that the 2 is our r and our theta is our 30 degrees. So how are we going to figure out what this is in rectangular form? Well, all you have to do is undo all of these polar forms. So in other words, we're just going to go ahead and figure out what cosine of 30 degrees is and figure out what sine of 30 degrees is, multiply all of that by 2, and what we'll be left with is our rectangular form. So what's the cosine of 30 degrees? Remember, 30 degrees is the same as pi over 6. So cosine of pi over 6 is root 3 over 2. Sine of 30 degrees, or sine of pi over 6, is 1/2, because we're in quadrant 1, so both of these should be positive. And if we multiply across by our 2, distributing it across, 2 times root 3 over 2 just gives you root 3, and 2 times 1/2, those cancel out, just giving me that positive I. So this is our rectangular form. So it's much easier to go from polar form to rectangular form than to go from rectangular form to polar form. Now, why do we care about this polar form? It's just as easy to work with the rectangular form. The reason we work with the polar form of complex numbers is because of a few theorems that we're now going to start developing. The polar form of a complex number provides an alternative method for finding products and quotients of complex numbers. So by changing a complex number into its polar form, you can pretty easily multiply any complex numbers together and very easily divide complex numbers together. It's much easier to do it in its polar form than it would be in its rectangular form. So here's what the theorem says. Suppose that you have complex number 1, z1, is equal to r cosine theta sub 1 plus I sine theta sub 1, and our second complex number, z2, is r times cosine theta 2 plus I sine theta 2. Then to get the product of these two complex numbers, all you have to do is multiply the two r's out front, and then you add the angles in between. So cosine of theta sub 1 plus theta sub 2 plus I sine theta sub 1 plus theta sub 2. To divide the two complex numbers, you divide the two r's, and this time you subtract the two angles. So pretty simple technique here to multiply and divide. Now we're just going to prove the product version of this, but the quotient part of the theorem would be proven in exactly the same way. So let's prove this theorem. So what we're going to do is we're going to multiply z1 times z2. And now z1 is this r sub 1. This should have a sub 1 here, and this should have a sub 2, because those could be different r's. So we're going to have r sub 1 times cos theta sub 1 plus I sine theta sub 1. So there's z1. And now we're going to multiply it by z2, which is r sub 2 cosine theta sub 2 plus I sine theta sub 2. And then to multiply these, notice that these are really just coefficients, so I can group this one together with our r sub 1 and just put those together out front. And then we need to multiply our cosine theta 1 plus I sine theta 1 times our cosine theta 2 plus I sine theta 2. And we're going to do that by just distributing. Good old FOIL. So I'm going to do cosine theta 1 times cosine theta 2. I'm leaving that r1, r2 out front of this whole FOIL process. So I'm just going to leave that part out front. And now we're going to do cosine theta 1 times I sine theta 2. So I'm going to put the I in front, and then cosine theta 1 sine theta 2. Then I'm going to do these inners, so that's another I, and it has a cosine theta 2 sine theta 1. And then I'm going to do the I times the I squared becomes a minus 1, so I'm going to change that I squared to a minus out front, and it's sine theta 1 sine theta 2. Okay, now that I have this all distributed, let's regroup these a little bit. I'm going to put this one and this one together because they don't have an I. And then I'm going to take this one, and I'm going to put those together after factoring out the I. So I'm going to pull the I out of both of these, and I'll be left with cosine theta 1 sine theta 2 plus cosine theta 2 sine theta 1. And then the rest of this proof is just remembering your sum and difference formulas for cosines and sines. Remember that the sum of cosine of theta 1 plus theta 2 is cosine of the first times cosine of the second minus sine of the first, sine of the second. And that's exactly what this is right here. Cosine of the first, cosine of the second, minus sine of the first, sine of the second. So these first two terms really are just cosine of that first angle theta 1 plus that second angle theta 2. Then you have to remember the formula for sine of a sum. Sine of a sum is sine of the first times cosine of the second plus cosine of the first times sine of the second. So it's sine 1 cosine 2 cosine 1 sine 2, which is exactly what we have here, but just in a different order. So this second part over here is just sine of theta 1 plus theta 2. So we've just proven it because that's exactly what this formula is up here. Okay? So now let's put it into practice. So here are two complex numbers in their polar form, and all we're going to do is come up with what their product is and what their quotient is, and we're going to leave our answer in polar form. So to get the product, all we have to do is multiply the two r's. So this 3 and this 5 are going to give me 15. And then inside, remember for a product, you're adding the two angles for both cosine and sine. So this is going to be cosine of the sum of this angle, 20 degrees, plus this angle 100 degrees. And then we're going to do the same thing for sine, and that's the one with the I in front. So sine of 20 degrees plus 100 degrees. So we get that 15 out front, and when we simplify here, we get cosine of 120 degrees plus I sine of 120 degrees. And we can stop here because it's said to leave the answer in polar form. So here's our answer. If we wanted it in rectangular form, then we would just figure out what cosine of 120 degrees is. Remember, 120 is the same as 2 pi over 3. Change those into your 1/2 and your root 3 over 2's, and then distribute that 15 across. But I'm going to stop here since it says we're allowed to use polar form. Now to get the quotient, very, very similar process, but this time we're going to divide the first r, the 3, by the 5. So we divide the r's, and instead of adding these two angles, we subtract. So we take the 20 degrees first and subtract the 100, and then we do that for the sine as well. So we can't really reduce the 3/5, it's going to stay that. But then 20 minus 100 becomes negative 80 degrees. Now there is one little technical glitch here, and that is the fact that our angle theta is always supposed to be between 0 and 2 pi for radians, or that would be the same as between 0 and 360 degrees. And negative 80 is a negative angle, so we can't leave our answer in this form because the argument isn't a positive angle. So all we have to do to figure out what negative 80 is equivalent to is just add in a 360 to it. So if you take negative 80 and you add in 1 revolution, then you end up getting positive 280 degrees. So in other words, negative 80 degrees, which would be in quadrant 4, is the same as cosine of 280 degrees, which is also a quadrant 4 angle. So it's just an equivalent version of that same angle, but within 0 to 360. So here's our final answer in polar form. Now another reason why we like to use polar form of complex numbers as opposed to rectangular form is because it's fairly easy to come up with powers of these complex numbers. So let's see what's going to happen. If we let z be r times cosine theta plus I sine theta, what would happen if we were to square z? Well, that means to multiply z by itself. And according to our product formula that we just came up with, that would mean to take the r times the other r, which if we're multiplying z by itself, they're both r, so r times r, and then inside you would be adding the two angles together. So this angle is theta, and if we're multiplying it by itself, then we're adding theta to itself as well. So this would be the product formula that we just talked about applied to z times z. If we simplify this, this becomes r squared, and theta plus theta becomes 2 theta. So z squared is r squared times cosine 2 theta plus I sine 2 theta. Okay, now let's take that result and use it to help us to get z cubed. Well, z cubed is a z times a z squared. So we're going to take the r of this z times the r of this z squared, which was actually r squared. So r times r squared becomes an r cubed. And then we take the angle of z, which was theta, times the angle of z squared, plus the angle of z squared, which was 2 theta. So theta plus 2 theta. So we just multiplied these two r's together and added these two angles together using that product formula. And what we end up with for z cubed then is that it's r cubed, parentheses, cosine of, and theta plus 2 theta is 3 theta. And so it's also going to give us an I sine 3 theta as well. So can you see what the pattern is? If we squared, we ended up with a square on the outside and a 2 in front of that angle. If we cubed, we ended up with a cube on that r and a 3 in front of that theta. So using a similar process, we would predict that z to the 4th should be r to the 4th, cosine of 4 theta plus I sine 4 theta. And this is actually called de Moivre's theorem. So if z is any complex number in polar form, r times cosine theta plus I sine theta, then z raised to any positive integer power would just be r to the n times parentheses cosine of n theta plus I sine n theta. So for example, let's find 2 cosine 20 degrees plus I sine 20 degrees, all raised to the 3rd power. So here, what we're really trying to find is, this is our z, and we're really trying to find z cubed. So if z is 2 cosine 20 degrees plus I sine 20 degrees, then according to de Moivre's theorem, z cubed should be 2 cubed, parentheses, cosine of 3 times 20 degrees, plus I sine 3 times 20 degrees. And if we simplify that, 2 cubed is 8, and 3 times 20 would be 60 degrees. Now we could stop here if it said that we could leave our answer in polar form, because this is the polar form answer. But this one asks for standard complex form. So that means what we want to do at this point is go ahead and figure out what cosine of 60 degrees is. And that's the same as a pi over 3. So cosine of pi over 3 is a 1/2, and sine of pi over 3 is that root 3 over 2, and they're both in quadrant 1, so those are both positive. Once we figure out what the cosine and the sine values are, then we just distribute our 8 across, and we get 4 plus 2 goes into 8 4 times, so this would be 4, and then I like to squeeze that I in between, and this would be 4i root 3. So this is the same answer as this one, but this is our standard complex form. Or sometimes we call it that rectangular form, or sometimes we call it that Cartesian form. Okay, now we're going to want to take 1 plus I quantity raised to the 5th. So this time, what we're starting with inside here, notice that is sort of standard form of a complex number. And you can identify that that x would be the 1, the real part, and the y would be the coefficient of I, which is also 1. Now in order to figure out what this is to the 5th, you have a couple options. One option would be to take 1 plus I times 1 plus I times 1 plus I times 1 plus I times 1 plus I 5 times. Now you could certainly do that, but that's going to be a little bit tedious to do. So that's where this polar form really comes in to help us out. Instead of multiplying this out 5 times, we could convert this to polar form first, and then use that de Moivre's theorem to figure out what this is to the 5th power, which is a really easy formula to apply. So let's do it that way, because it's going to save us a lot of time. Now to convert to polar form, we're going to have to figure out what that r and that theta are equal to. So how do you get r again if you know x and y? Remember, r is just that hypotenuse of that right triangle. So r is defined to be the square root of x squared plus y squared. So 1 squared plus 1 squared is going to be 2, so r is square root of 2. And then to figure out your theta, what you do is you use, again, that right triangle relationship where sine of theta was the y over the r, the hypotenuse, and cosine of theta was the x over the hypotenuse r. So sine of theta here would be y, which was 1, over r, which was root 2, and cosine of theta would equal x, which is 1 over root 2. And if you rationalize that, remember that's the same as root 2 over 2. So what angle has the sine and the cosine value both being positive root 2 over 2? That's going to be a quadrant 1 angle, and it's a nice angle. It's just our pi over 4. Now you can use pi over 4, or you could use 45 degrees. Either option. So now we know what r is, and we know what theta is, so we now know what z is in polar form. It's going to be this r, which is our root 2, times cosine of our angle. Now, Most of the examples in this problem use degrees, so I'm going to show you one with radians. So I'll leave it as pi over 4 plus I sine of pi over 4. So this is the polar form of that angle. Now the reason we do that, I mean that was a little bit of work to come up with that polar form, but not a whole lot. It wasn't too tricky. The main reason we do this, to get this in polar form, is so we can use de Moivre's theorem, which says that z to the 5th then would just be this root 2 to the 5th, parentheses, cosine of our angle times 5. So 5 times pi over 4 plus I sine of 5 times pi over 4. Now what's root 2 to the 5th? You can figure that out by just expanding it out. These two give you a 2, these two give you a 2, and we're going to have 1 root 2 left over. 2 times 2 gives me 4 root 2. So root 2 to the 5th simplified is 4 root 2. And then cosine of 5 pi over 4 and I sine of 5 pi over 4. Well, we know that that's a pi over 4 angle. So since we're trying to convert this back into standard form, we need to figure out what this is equivalent to and what this is equivalent to. They both have to be root 2 over 2's, but we need to figure out what the signs should be. And if you think about 5 pi over 4, that's over here in quadrant 3. And in quadrant 3, they're both negative. So I need to make those negative root 2 over 2's. To finish it off, just distribute your 4 root 2 across. This 2 will go into that 4 twice, and a root 2 times a root 2 is another 2. So 2 times that 2 is going to give me minus 4. If we do it again, times our root 2 over 2 over here as well, you're going to get exactly the same thing. So 2 goes into 4 twice, and this root 2 times that root 2 is another 2, and it's going to stay negative. So this will be minus 4, and then that I goes next to it. Okay, so by converting to polar form first, it made it much simpler to raise it to that 5th power so that we didn't have to distribute this across 5 times. Now the last thing we're going to talk about is another reason why we use polar form as opposed to standard form, and that's to find roots. We just talked about de Moivre's theorem, which enables us to find these complex numbers raised to integer powers, so z squared, z cubed, and so forth. Well, what if we wanted to know the square root of z, or the cube root of z, or the 4th root of z? How would we figure that out? And there's a formula for that. So here's what it looks like. We're going to focus now on finding roots of complex numbers. If w is a complex number, then the solutions to z squared equal to w would give the 2 complex square roots of w. The solutions to z cubed equals to w would give the 3 complex cube roots of w, etc. So there's 3 solutions to this equation, there's 2 solutions to this equation, and those are giving us either those square roots or those cube roots. So if we let w be r parentheses cosine theta sub 0 plus I sine theta sub 0, and that's any complex number, and we let n be any integer greater than or equal to 2, then there are going to be n distinct complex roots of this complex number, and this is how you would figure them out. So you're going to call them z sub k, and this out front is the nth root of that r, just kind of like what you would expect if you were trying to take the nth root of this complex number. But then look at what happens to the angle. You take theta sub 0 divided by n plus 2k pi divided by n for both the cosine and the sine. And we let k range between 0 and n minus 1. So you're going to get a list of different solutions here. If you were looking for example, a cube root, then you would get a z sub 0, a z sub 1, and a z sub 2, and you'd get 3 different cube roots. If we were looking for a 5th root, then we'd get z sub 0, z sub 1, z sub 2, z sub 3, and z sub 4, and that would total our 5 5th roots that we would get. So it's a little bit tricky to understand just by looking at the formula. Let's go ahead and try an example. So this time we want to find the complex cube roots of -1 plus square root of 3i, and we want to leave our answer in polar form with the argument in degrees. So again, to try and take the cube root of this doesn't seem very easy to do, but if we change it to its polar form first, then we'll be able to apply this formula and come up with what our cube roots are equal to. So first we have to change this to its polar form. So we're going to write it in polar form first. That means we need to figure out what our r is, and here in this standard form we know that the x is -1 and the y is the square root of 3. So r is the square root of x squared plus y squared, and if we simplify that we get 1 plus 3 underneath, which is square root of 4, so r is 2. To get our angle, sine of theta is the y over the r, and cosine of theta is the x over the r. So in this problem, y was √3 and r was 2, and x was -1 and r was 2. So what kind of an angle is it that has the cosine being -1/2, and the sine being positive √3/2? First of all, what quadrant would you have to be in if your cosine is negative but your sine is positive? Well, that only happens in quadrant 2 on your unit circle when the x's are negative and the y's are positive. So we want a quadrant 2 angle, and these are nice values that you should recognize. This is the same as 2 pi over 3. It's a pi over 3 angle because the cosine's a 1/2 and the sine's a √3/2. Now, we are being told to use degrees in this problem, so 2 pi over 3 is the same as 120 degrees. So now we know our r and we know our theta, so let's rewrite our complex number in its polar form. This would be 2 out front, cosine of 120 degrees, plus I sine of 120 degrees. Now we want the cube roots. So we want this n up here, right up here, to be 3. So this is what we're going to get, and it's again a little bit tricky to see how to use this formula, but what you're going to do first is to come up with sort of a general formula for z sub k, and we'll talk about what that k is in a moment. But for now, just leave it a k, and we're going to plug in everything else that we know. We know we want a cube root, so we know we want this little index here to be a 3, so this needs to be a cube root of 2. And then for the angles, we're going to take the original angle, theta sub 0, which is our 120 degrees, and we're going to divide that by our n, which is this 3 again, and then we're going to add in 2k pi over n, but instead of using 2 pi, because that would be radians, I'm going to use 360 degrees times k over n, which is our 3 again. So this is what it would look like. It's the original angle, 120 degrees, divided by 3, and then it's 360 degrees times k divided by 3. And then we're going to do exactly the same thing for the sine. So this would be 120 divided by 3 plus 360k over 3. So we get this formula where we're leaving k in there as kind of a variable. I'm going to simplify it just a tad, and then we'll talk about what we do with this k. So if we simplify, 120 divided by 3 is 40 degrees, and 360 divided by 3 is 120 degrees times that k. So we have 40 degrees plus 120 degrees k. So here's our general formula. Now what we're going to do is we're going to let k range between 0 and n minus 1. And remember, Rn was 3, so 3 minus 1 would be 2. In other words, we're going to let k range between 0, 1, and 2. If I went and let k be 3, then 120 degrees times 3 would be 360 degrees. So we're looping back around on our unit circle and coming back to these original 3. So we don't want to go as high as 3, because then we're going to start repeating answers here. So it's just k being 0, k being 1, and k being 2. So you go up one less than the kind of index you're looking for here. So let's see what this would look like. If I let k be 0, then z sub 0 would be the cube root of 2, and then this would become 40 degrees plus 120 times 0. And obviously that's just going to go to 0 for both of these. So what we end up with is z sub 0 equals cube root of 2 times cosine of 40 degrees plus I sine of 40 degrees. So that's our first cube root. And there should be 3. By this fundamental theorem of algebra, you're going to have 3 solutions, 3 distinct cube roots. So now let's do this again for k being 1. So this is going to give me z sub 1. I'm not doing anything to that r out front. It's going to stay cube root of 2. The only thing I'm doing is I'm multiplying this 120 by whatever k is. So this time we're going to get cosine of 40 degrees plus 120 times 1. And if you simplify that, we get 120 times 1 is 120 plus a 40, so this becomes cosine of 160 degrees and sine of 160 degrees with that cube root of 2 out front. So z sub 1 would be this cube root, this answer. And finally, if I let k be 2, then z sub 2 would also be cube root of 2, but now we're going to take that angle and we're going to do 40 degrees plus 120 times 2, because now k is 2. So if we simplify that, we get cosine of 120 times 2 is 240, and 240 plus 40 is 280. So here's z sub 0, here's z sub 1, and here's z sub 2. And this is where I would stop, and the reason why is because, again, if I let k be 3 right here, we'd get 120 times 3, which is 360, and 360 degrees plus 40 degrees is equivalent to just 40 degrees. So it's going to give you the same solution as this z sub 0. So if we were to keep going, we would keep recycling through these 3 possible answers. Now, I want you to visualize a little bit about what this looks like on a graph. So if you were to graph these, this is what you would see. Our z sub 0 was cube root of 2 for the r, and the angle was 40 degrees. So that would be somewhere over here, where this distance is that cube root of 2. Then cube root of 2 and cosine of 160 and I sine of 160 for k equals to 1, 160 degrees is over here in quadrant 2. And again, this would be cube root of 2, and this whole angle from here to here would be that 160 degrees. And then the third solution that we got was also cube root of 2, but the angle was 280 degrees, which would be just past 270 over here. So this would be 270 all the way across to here, and that magnitude would be cube root of 2. So they all 3 share the same magnitude. The only thing that's different about these 3 solutions is the angles are different. And what you want to notice is how are they different. Notice that each one of these is separated here by 120 degrees. And they're all equally spaced. All 3 solutions are equally spaced around our circle. If you can visualize a circle here of radius cube root of 2. So if you can visualize that, you just have these 3 answers that are all equally spaced 120 degrees apart from each other. So it's like 3 different radii of that circle, and I didn't draw a very good circle at all, but use your imagination there a little bit. But it would look something, kind of like this. So there's my solutions. If you had wanted to find, say, a 5th root instead of a cube root, then you'd have 5 different solutions in here that would be equally spaced throughout 360 degrees as well. So you'd get 5 little spokes on your circle that were all equally spaced around. If you wanted a 7th root of z, you'd get 7 solutions, and they would be 7 different solutions that all had the same radius, but they would be 7 different spokes equally spaced around this circle. So that's what you want to keep in mind. You're always going to have exactly as many roots as the index. So if I want a 5th root, I'm going to get 5 different solutions, 5 different roots, 5 different z's, and they will all have the same r based on that root of your r, so cube root of 2 or 5th root of 2 or 7th root of 2, whatever the problem was asking for. And the only thing that would be different about them is that they would be different angles, so that they were all equally spaced. Okay? Alright, so the polar form of these complex numbers do allow us to find different powers and different roots, different products, and different quotients very, very easily using polar form as opposed to using that standard form. So that's the benefit of learning about how to convert a complex number into its polar form. Alright, that concludes our lecture on the complex plane and de Moivre's theorem. Good luck!